production with machine learning on the beam. Last year, I gave a talk at ElixirConf in the US, talking about how we were betting on using Elixir, going all in on Elixir for machine learning. And now we're a year later, and I want to kind of reflect on how that's gone, what we've learned, and what we've been able to do. So that kind of answers a little bit of this question: who am I? What am I doing here? Which is a question I ask myself more often than I should, probably. So I'm the founder and CTO at a company called Amplified. I'll tell you a little bit more about it in a bit, so I'm not going to go into it too much right now. But I am an economist, and I turned into a data scientist. A lot of what I was doing as an economist required working with text, and machine learning is a little bit more powerful for doing that. I ended up doing a fair bit of consulting on things like causal models and impact evaluation for like using econometric models for various governments. And that was how I was kind of working, or how I was working during my PhD. I ended up dropping out of my PhD to start this company, but I'm not a super proud PhD dropout. I actually really loved academia and doing all of that. And yeah, the other thing is I'm involved in the EEF machine learning working group, which has been really exciting. So yeah, PhD. I was working on the relationship between innovation and climate policy. I was trying to do a new approach with machine learning. And you know, who said nobody ever gets to share their PhD work? It gets hidden, right? The reason why this is relevant is because what I was working with were patents. I was trying to understand the way that climate policy can affect the direction and rate of innovation. So rate can be measured with things like the number of patents, and direction can be measured with usually the classification codes that are associated with those patents. That was the way that people were doing it before. I found this frustrating. It just didn't capture enough information. And I was looking at these patents, and they have so much information in them. They have so much text. This is around, I mean, that bit was from 2015, but this is, you know, around 2014, 2015. And I've started to see these kind of models emerge, like Word2Vec, Doc2Vec, people starting to do a bit, you know, with machine learning with text. And I thought to myself, okay, how can we get this information that's in these patents into these econometric models that I was trying to use to understand the kind of like rate, pace, innovation, right? And the answer is vectors. The answer is that we end up with we can represent all of that textual information into numbers, right? We can take all of this stuff and put it into something that a computer can understand, okay? And while I was working on that, I got a call from a friend of a friend, wanted to meet up for some drinks to talk about patent stuff. He was working in IP consulting, and he came to me, and we had some, you know, lovely wine in London, chat about all this stuff. And he started talking about this, which is prior art search. That was the kind of first thing that he did. I know if you've never dealt with patents before, prior art is what we call the things that already exist, right? All the patents that already exist in the world. If you invent something new, you need to determine whether or not it actually is new. You have to go and you have to look through all of those patents, all the existing patents in the world, and say, hey, this thing that I've done, it's novel for these reasons. It's actually something new. But it was really painful. So this is what Sam, my co-founder, hi Sam, was saying about, he's not here, yeah. What he was saying about you know, he was saying that there were all these problems, and this kind of lays it out. This shows like what the timeline of a prior art search might look like for a corporation, right? So you've got the inventor, and they know what they're doing. They've described their invention in an invention disclosure. That goes to get reviewed by some IP person. The IP person or the lawyer might go order a search from a search firm. You might have, you know, 50 PhDs, you know, somewhere else in the world who are going to sit there and they're going to read 5,000 patents for you, 2,000 patents for you, and tell you which ones are the most relevant, which ones might invalidate the thing that you've created. It's really, really painful. It's a big convoluted task. And on top of that, we have been, the way that we actually go and determine what that prior art is really outdated. It's really, really difficult. Search is a tough problem, and there are over 100 million unique inventions in the world. 100 million. So to go and actually find what's relevant in that is an incredible task, okay? And the way that we used to do it and the way that we do it now, it's kind of evolved over time as this number has increased, right? So patents are a relatively new thing in the past couple hundred years. And through time, it used to be literally documents in shoeboxes. You had people going through and saying, okay, I'll take down this shoebox and I'll look through and I'll look through and I'll figure it out. Then as things started to improve, you started to do things like Boolean search. You started to be able to say, hey, I've got keywords. I know I can do cool things with these keywords. I can find this keyword within 3 words of this keyword and move on from there. But as the number of patents in the world gets bigger and bigger, this gets more and more challenging. And it's not always accurate, to put it mildly. So what people will do, patent attorneys will do, is they'll try to write their patents such that it's actually difficult to find. There are benefits to making it a challenge for your competitors to find your invention, because the kind of the promise or the contract in patenting is that you disclose some secret, some invention that you've done in return for protection. You get a monopoly on that invention for a certain number of years. And the problem with that is that you can actually go and build on that, like your competitors can go and build on that. So we call this spillovers in economics. And it's a really big boon to society. It's actually a good thing for society. It's the whole point of the patent system, is that you disclose your inventions and other people are able to build on it, and you can, science moves forward. But from a competitive perspective, as a company, you don't want your competitors to be able to do that, okay? So what you do is you try to hide it. And when you do that, it makes it really difficult for everyone to find it, including the patent examiner. And then you have issues where people invent things, people then sue them because they said, oh, you infringed on my patent, and there's a whole problem with this. So we thought, well, can we leverage this, this technology, the way that things are changing, these ways of representing patents, to search, to improve this process? And the answer is yes, we could, which is why I'm here. So this is kind of what the process looks like now, and what Amplified has become is a patent information platform. We've eliminated this overhead. We've kind of tried to democratize things, move the power into the hands of the inventor to move things further, earlier in the process, and allow people to build on the knowledge that they build up. All of these different wonderful things that you can do for patents. But it kind of came out of this original prior art search problem, and it's still centered on this idea of search and similarity. So let's talk about search and similarity. How do machines determine document similarity? I mean, who here is doing any work in machine learning? Raise your hand. Couple of people, not many. Who here knows what a document vector is? More people, right? It's becoming more and more popular. We're talking about it more, with ChatGPT and generative models, AI. It's in the news. It's something that you're aware of, right? But you may not. It may be a bit foggy. You may not be really clear exactly how. Ask a computer. Well, you can now, I guess, with ChatGPT. But you can't just ask a computer. Are these two things similar? Are these two documents similar? Figure out the meaning of the raw text as is. I mean, we can do things like string similarity, but okay. So what we do is we convert the text to a vector. We'll talk a little bit more about how we do that in a bit. And you have to have a way of getting good vectors, right? A good representation of the thing that you care about in the underlying document. You then want to basically embed this like larger information that you have into these documents, align them such that you can search with them. And then you might just get really excited and you say, okay, we can turn patents into vectors. We've got this power. It's a superpower, right? What do you do? So you've got this little guy up here who's saying, I'm turning a patent description into a vector. Great. And another one, it's like King Midas at this point. Everything you touch is turned into a vector. Vector, vector, vector. It's like Oprah. You've got a vector. You've got a vector. And you get a situation where you've got 100 million specifications that are stored in a vector space, and now you have a vector database. So you want to be able to search within that database. What you need to be able to do is you need to be able to take something like an invention disclosure, this idea that you have that you can describe in natural language, and you need to embed it into the same vector space. It needs to be able to match up with the things that you already have, okay? So you can kind of see here that we've got, all right, we're pointing up and we're saying, all right, here's our place here, and now we want to search around it, okay? We want to find the things that are similar, that are in a similar space, okay? And we want to display them in the order of distance. This is really useful because as opposed to something like keyword search, you're never excluding anything. You don't have this problem that you had before where you've come up with all these complex Boolean search strings, but you're still missing things that might be similar because someone wrote and used, they use language that other professionals just don't use. Or, it's a different research group, or it's another language entirely. If you restrict in that way, then you are going to lose things, you're going to miss things, and then you're going to be sued later on, potentially, right? So what we want to do is we want to get it into a technology space, right? And so now let's go back one. I'm going to show you. So, okay, we're looking over there, and then we're going over here, and we're saying, are we changing the input, and it's going to move, and you're going to find different things, right? So the vector database, all the things there stay the same, and your input moves, so you go and find things over there. Right. And at Amplified, we're combining this with traditional search. So you're still never excluding anything, but you can still do things like filter by metadata. You can like look on by assignee or keywords if you want to. If you want to filter by those keywords to try to like pinpoint something specifically, you can do that. Dates, etc. But the ordering remains the same. So, okay, I'm going to take a quick little trip back in time. So I want to set the scene for you. I'm going to move this away. My beard is rubbing on it. I apologize. So it's late 2021, early 2022, and I'm the CTO of a fast-growing startup. We've gone all in on LiveView, and the team is loving Elixir. But we still use Python for machine learning and extract, transform, load, ETL processes because that's just what you do at this point in time. Python is the 5,000-pound elephant in the room, or whatever idiom that is with an elephant. And we're hurting. We're hurting because of this. There's a big wall between app development and data development, data engineering, data science. And if you're a big company, that's kind of expected, right? You've got different teams. All these different teams are working on different things, but we're tiny. And so, and we're all remote as well. And we're meant to be an AI-powered startup. We're AI first. We're doing a data engineering, data development, and data science. That's like core to what we're doing. And yet there's this inability to kind of talk across these silos. So it's just hurting. We've got a lot of brain power that's going into how do we deal with these things. We're slow getting from idea to a feature. There's a bunch of cruft. It's just part of this is the isolation. We needed to make a change, right? I'm going to step back just a tiny bit further. So back in 2020, I was experiencing a similar issue with front end and back end, right? So we were using Phoenix for our back end, and we had an SPA React front end. And we were struggling with kind of similar things. We had people who were really, really good at the front end side of things, JavaScript, and people who were really good at the back end side of things with Elixir. And we had to deal with, as a small team, writing these complex contracts, the API surface, et cetera, and passing this data back and forth. And we're using so much data. It's just a big challenge, right? And I knew that live view existed. I knew that it was cool. I didn't know if it was ready. I took a weekend and rebuilt one of our kind of core views in live view, and it was just incredible. It was an amazing experience, and I was just boom, immediately we went all in. We just went for it. And we hired Dashbit. They helped. It was early. We adopted it, and we just went to town. It was the best choice that I have made as a CTO up to that point. Yes, it was fantastic. So I'm feeling this pain back in late 20, we'll move back up to 2021, 22. I'm feeling this pain, and I know that there's something brewing. There's something there that might be able to help. Whee! And so I went and tried some things out. I was very, very excited. So this is, early days. This is NX. We've got Axon. It's come out. I wanted to try some things and see what we could do. And this is kind of before Bumblebee. So Onyx is a machine learning runtime. Axon is a machine learning, a deep learning library, a artificial intelligence library that's built on top of NX. What I was able to do is convert a model that we wanted to use into an Onyx specification, and then load that in to Axon really, really simply. It was fantastic. Okay, so I was able to take our machine learning model, and I was able to load it into Elixir. And then, so this moment at which I could actually do that, and I could generate a vector with Elixir rather than with Python, was that similar kind of experience, that similar kind of moment that I had with LiveView, where I said, all right, this is what we're going to do. This is the way to go. So we decided we're going to do it, but the problem that we have is that we don't just need to do it, one time or 10 times or 100 times. We need to do it 120 million times, right? We needed to do it in bulk, and we have this situation, right? So I'm gonna lay it out for you. We have patent offices who are sending data to our data supplier, who send things to a data warehouse, and then we've got to do something with it and put it into our search base, right? Seems not that bad until you get to this. And when you see this at the top of a 20-page official document, you know that you're in trouble. XML is a thing. Patents are provided to us all in XML. Broken up XML, for that matter. So we've got this Postgres database. It's got this star-like schema. Every spoke in the Starlight schema, the star-like schema is XML content. There's weekly updates that are staggered across the week, and we've got customers who care about those things coming in as soon as possible. So we need to get from this to vectors in a vector database, along with metadata, full text search, and being able to do that vector similarity, right? We've got to prep the data for ingestion. We've got to embed it. We've got to index it for that keyword search, and we've got to index the metadata for filtering. Okay. So we're doing all of this at this point in time in Python. And oh my goodness, we were doing a whole bunch of imperative XML parsing, going through and saying, all right, I want to find this bit in XPath, and I want to find this bit, and then maybe, it might be missing. It might not be exactly what we expect, et cetera, et cetera, et cetera. And I actually had something come to the rescue, which is not a Beam language, which is Rust. But Rustler is an amazing project that allows you to write things in Rust and bring it into Elixir. So for the XML parsing, thank you, Rust, we can do things in a declarative way. We can define what we expect, and we can parse the XML in a much simpler way. We can actually identify the things, the format that we want it to be in, and we can deserialize that into Elixir really readily. Fantastic. Okay. Now what? Broadway. So the kind of issue that you have when you're doing 120 million and you're updating millions at a time is that you need to be able to, you need to be able to spread that work out. And Broadway makes that super, super easy. So, you've got concurrent multi-stage data ingestion, data processing pipelines. We're able to basically chuck things into RabbitMQ, millions of identifiers at a time, and then pick them up with Broadway. And Broadway is, then within our Broadway processes, we're able to do that kind of ETL work that I showed you with Rust. And we're able to use Axon and Axon Onyx to embed the documents. And we've got a really great situation. Okay, so let's talk about this a year on. What did we get from this? When I did my talk at ElixirConf, I said, we were able to cut down on the cost, on the time. We were able to do it all in Elixir, aside from a bit of Rust, but the Rust is going via Elixir. So what have we done? We've eradicated Python completely. We've got no more Python. In fact, everything that we do is in a monorepo, which makes some people go, and other people go, yay. And it makes me go, yay. We're a tiny team, and it's great. We have slashed our AWS spend in half. Without admitting exactly how much we spend, that amount accounts for 5 figures. For a small startup, that's a ton. When thinking about Python as well, I just want to go back up there. One of the benefits that we got, we have no more siloing with this. We have no more context switching. We have no more, I'm going to build this over here and then try to translate it over here. We have no more, I'm going to deploy another service that has to do 15 other things. We've got a tiny team, and we can do everything in Elixir. It's the cross-pollination, the ideation, and getting to the feature development is just wild. Yes, so we've got faster bulk loading. Why does this matter? So we can go from 0 to 100, but once you're at 100, it shouldn't be such a big deal. Except if you want to train a new model and try to do something new, you then have to go and re-embed everything, right? So being able to do that in bulk and getting it up into our vector database is just massive. We've got way more observability, and I want to give a shout out to the work that people have been doing on telemetry and the work that people have been doing on open telemetry. The EEF group on observability has been incredible. We're cooking with gas. We can see so much more. Grafana has been excellent for this, and we can kind of, again, circle the wagons. We're doing things all in Elixir. We're able to borrow. We're able to do code sharing, and it just works. It just works. We were fighting so much before. We had to allocate fewer resources for the Python stuff, even though that was really like our core value proposition, because we had to spend money and time working on our application. And so now we can just allocate all of our time on one thing, on one programming language, on one kind of team. We work as one team now, and it just works. And just so you can see kind of like how simple it is and how it works, I'm kind of annoyed with Mermaid.js for giving me pixelated things. I apologize. It goes from our data warehouse, and it's actually the monolith that's picking up the changes from the data warehouse. And we've got our monolith for our application. It's then sending all of that to RabbitMQ, which sends stuff to ETL, which sends stuff to the search database that the monolith then uses. But you can see there's some arrows going back from ETL to RabbitMQ into the monolith as well, and we're able to actually let the monolith know very easily what's been processed by the ETL pipeline, because it's not always what goes in, what comes out. There are some changes and updates, and we want to let the monolith know when things are ready. The benefits have just been huge with this. Part of this is that we can very rapidly go into our code with the monolith, and we can queue up things to change them. We don't have to do a full ETL run. It's all happening streaming rather than in these kind of bulk prefect runs that we were doing before. Now, of course, you could emulate something like this using another programming language, using Python, but it's just more work, and the ability to kind of share knowledge and what we're doing is incredible. So let's talk about what we've done over the year since. That's great. I am super happy with what we did, but there's more. And wait, there's more. So all of this was laying foundations, right? So it was really, really cool that we were able to do this. We were able to make this change. We were able to rid ourselves of external services, like all this stuff, right? But we knew that there was so much more that we could do, and that there was more that was starting to become readily available in Elixir. And things that we could do without deploying Python services, without dealing with API contracts, without doing all the engineering alongside it. We just build features. So I'm going to cover 2 features that we built and talk a little bit about how we were able to do that because of Elixir. So you guys know there's the value, effort, value, whatever words you want to use for these different things, difficulty and reward and all that stuff. So we've got these two features that I'm going to talk about. One of them is called custom classifiers. One of them is map visualization. It'll become clear what both of them are in just a moment. And for a long time, we knew that they were really valuable, but they were just kind of a pain. They were kind of difficult. We were like, oh, well, we're going to have to build another Python service, and we're going to have to go and do all this, and we've got to feed it data from here, and we've got to give it access to this database and all of that. And the change has been that over the last year, this has happened. They moved over there. And so we built them. So I'm going to start with custom classifiers. Just before we can discuss them, you need to understand why we wanted to build them, why they mattered. So I'm going to give you a quick introduction to kind of what a project looks like in Amplified. So this is what you get when you land on a project. You have your kind of search inputs there on the left. So you've got your invention description. You can describe the thing that you're looking for in natural language, and then you can add filters, keyword filters, class codes, et cetera, et cetera. On the right, you have your search results, okay? And you're going to work through those search results to try to determine which ones are relevant and which ones are not. So I have a pointer here. You can see we've got like checkmark, flag, reject. And you can work through, basically, and say, all right, this one's relevant, this one's not, this one's relevant, this one's not. This one might be relevant. I'll come back to it, okay? So patents have lots of data, as we've discussed. And companies also have lots of data. So this is the thing. Patents have metadata, but companies also have lots of metadata about patents. And it seems reasonable that you might want to bring those 2 things together. So we gave companies the ability to tag patents. You said, okay, we can click here, add a custom tag, and you can add it. So in this one, I'm going to talk about quantum stuff here. I understand none of it. I'm an economist. I'm not a physicist. But one of my co-founders is a quantum physicist, and he knows more than I do. So, all right, we've added a tag to this patent, right? That's cool. I'm excited about that. But you've got 100 million patents. You haven't tagged all of them. And when you're searching, you might be working with a couple thousand at a time. You want to be able to predict whether the patent should have the tag, right? So what have we done? We've given our users a way to bulk upload their tagged patents. So what you're seeing here are patents that have been tagged with qubit generation. And what we then do is we take the ones that they've uploaded. They've said, yeah, this one yes, this one no, this one yes, this one no. And we've given them the ability to train classifiers. And you see on the left, we've got kind of like how that classifier is doing over time. We've got some metrics over here. You've got the ability to change like where the cutoff is and to retrain, okay? So you go back to your project, you click predict tags, and all of a sudden you have on all of those patent results that you were looking at, you can see the predicted score. And you can see the color, green or red. Is it really likely to be this one, or is it not? And then you don't want to stop there, right? Like, so what makes this powerful is the ability to go and then sort your result set by the predicted tags. So our customers have saved like 85, 90% of time reviewing patents by doing this. And you can then use it to train the model further. So we're really, really excited about it, really excited about the feature. So what do you need to build a feature like this? You need the vector representations of the documents in the first place. So you're not gonna go and train a a full like end-to-end deep learning model for each customer, for each tag, for all of those things. You've already got these good representations of the documents. You can feed those into traditional machine learning models, right? You need a way to train those models, you need a way to store those models, and then you need a way to predict on new documents. So I want to start by thinking about how you might do this with something like Python, right? Python's, again, the big elephant in the room. So if you've got an Elixir monolith, you've got a Phoenix application, and then you need to do this in Python, all right, so you've got to create a Python service, okay? Then you've got to give it access to your vector database. You've got to replicate the queries that you were doing, even really simple ones, to go and get those vectors from your vector database or from the additional work. So you've replicated work already, all right? You already have those vectors in memory. Now you've got to go and get them in Python or send them to Python, which is quite a hefty network load. So then you need to train the models. You use sklearn, and that's kind of the idea here, is that you want to be able to use sklearn, scikit-learn. So you need to somehow share the tag information with Python. So you've got to share your training set you've already got. All right, you might give it access to the application database. You might send it the data across. It kind of depends, right? Again, replicating work. You've got to store the models. You might do that with S3 or MinIO, something like that. You've got to replicate work again because you probably are already working with this in your application, right? But another library, more access shared. You've got to do more. It's not this simple service anymore. It's something that's kind of grown into basically a second application. Then you need a way to predict on those new documents, right? You're going to have this services running. You're going to send your search information across, even though you've already got it sitting in a process or a view in your live view application. You need to load the model into memory. You need to serve predictions. You might need to juggle a whole bunch of models. You might only need them sometimes. You'd like to dynamically stop and start those serving processes, probably per model explicitly, and maybe you want to scale them, right? And all of this that you're doing is really just because you want to use scikit-learn. You want to use a model in scikit-learn. That's the core of what all of this has been. So what do? Hey, there's a solution for that. There's something in Elixir. So Scholar has emerged over the past year. It's a library for more traditional machine learning. It runs on NX. So this is really cool. You can serialize models with nx.serialize. At the end of the day, it's just tensor representations under the hood. You can serve models with a thing called nx.serving, which has been one of the most exciting things over the past year for us. It encapsulates the client and server work and does automatic batch accumulation. It's a super, super excellent thing, and it's running in processes, right? You can explicitly spin up these different model servings under a dynamic supervisor whenever you want, and you can set a hibernate after parameter to minimize the memory when they're not in use. So you can spin up 1,000 different models. They're all quite small, but when they start building up, you can either shut them down or you can, like I said, use hibernate after. You can distribute them across nodes, and if you're using GPUs, have multiple GPUs on one machine, you can actually distribute across those GPUs as well. It's just been incredible. And hey, there's a bonus as well. If we stick these models in the monolith, then we can also broadcast progress to our view using PubSub. There's no infinite spinners. We know exactly how far we've gotten along, which is really nice for our customers. It's been surprisingly one of the things that they have flagged the most. They care about progress. So we need a way to shrink down that vector into 2 dimensions and put it on the screen. But I want to talk a little bit more about what's going on here. So you can see here we've got these different clusters. different colors, and they've got labels. So if you're doing a patent search, you can come in and you can really understand in a much richer way what you've got and the different ways that things kind of interact and are similar to each other. You can go through and scroll over, and we can do this. It's interactive visualization, so you can go through and kind of scroll over each dot and see what they've got. You can change the color by information, shape by information, and change different aspects of the metadata to understand your search results. And going back to those classifiers that we had before, you can actually visualize the score of those classifications. You can see these different pockets, right? So over here, you can see that these things are not very similar to the tag that I have, and these things over here are very similar to the tag. Right? These are the highest predicted ones. So you know that you might want to zoom in over here and explore this bit over there. Okay, so what do we need to build this? We need vector representations of the documents. We've already got them, right? We need something like tsne or umap, which is a way of reducing the dimensionality down to 2 dimensions so that we can plot that on the page. We need a library for plotting it on the page, right? So tsne or umap, you're probably going to reach for Python again. Scikit-learn, something like that. A way to plot that on the page, wow, now you've got to start talking about JavaScript as well. So you might have to, you might have a separate view. You might actually build a small, JavaScript application, something like that to actually get the JS on the page, and you've got to pass that data back and forth to the JS visualization, et cetera, et cetera. And then, we've also got those labels that I showed you before, so you might need something, a generative model, something like that. We'll get into that in a bit. Scholar saves us again with this. Scholar has tsne, and we can do that dimensionality reduction directly in Scholar. And we've also got another library that's out called Vega Lite, which are Elixir bindings to Vega Lite, which is a plotting library for JavaScript. And what's really, really amazing about it is that you can construct and send that specification via your live view, right? So you can dynamically construct the JavaScript specifications with the visualization and send them up to the view all in Elixir. This has been amazing for us. It's been incredible. So what's the big thing? What's the force multiplier? What's the thing that has kind of threaded through this and changed the way that we work and changed changed everything? We've got all of these benefits that you've seen. We're able to really circle the wagons. We're able to use Elixir for just about everything. We've got a really small team. This has been great. Features are faster to build. They're less technically convoluted. There's a secret weapon, okay? And it's as I said, it has changed the way that we work entirely. We can do crazy fast prototyping. We can deploy that for our non-technical colleagues. We can demonstrate things. We can access running systems and not necessarily change them, which for us, when we're dealing with these kind of really massive convoluted ways of interacting with data, is incredibly powerful. Livebook. Who here is familiar with Livebook? Yeah, because it's awesome. So with the classifiers, I can't show you the live books for those, but we were able to actually work with our customers and work through live books to create the actual end product. We were able to produce deliverables long before we ever touched the application code. And I've worked like this before, right? Like I've prototyped things in R, I've prototyped things in Python, I've delivered reports using those languages, and then I have to go and translate it all into Elixir for the application code that I've got. We're literally copying and pasting at this point when we've got Livebook. So I'm just going to show you very quickly. With map visualization, we did a really cool thing, and we're doing it again with a new prototype that is, let me see if I can go to full screen. Nope, that's just fine. We're doing it, this isn't on that screen, that's why. Okay, 1 second. Can I go over to here and switch back to here? Nope, here. There we go, hello. Cool. Okay. So, yes, so with the map visualization, this is kind of a similar thing to what we did. We have a ton of data that we need to move across, and we'd like to be able to access data in production systems, in running systems. But we don't want to have to change those systems, and we want to be able to iterate on what we're doing. So what I've been able to do is define a Livebook, which has keynote, which are like rich inputs and outputs. And I can go over here, and I can open up and deploy it as an app. Now, this is running on Fly, and it has access to our running production systems. And so what I can do is send this to my colleague, Sam. Hi, Sam. And he can go through and he can play with this. He can start to work on and understand the different ways that we're gonna show this. So he can look at this and say, maybe I actually wanted to display that cumulatively. I'm going to submit. And these are the kind of levers that we might want to show our customers. And he can give us this early feedback and allow us to understand what it is that we need to change. And we can just, pop back over into the actual Livebook, and we can make those changes that we might want to make to the actual visualization prototype that we've got here, which, by the way, we're using Explorer, awesome. And we can make those changes, and we can very rapidly then deploy it back out as an app again. So let's say, I actually decided that I don't want to exclude the other bit here. So I can just very rapidly change that, go over here, press deploy again. We've got a new version. Go back, new session, and what you might see is once this loads, we can have a look here, and you can actually see, we can see everyone else now. So this was like top 10 assignees, and now you can see top 10 assignees and everyone else. I'm very excited about that. Okay, let's see if I can get us back to this one. Is this right? Nope. Okay, 1 second. So let's go back to the view, play slideshow. There we go, we're back. No, we're not. Why do you lie to me? There we go. Nope, other way. Nope. Okay. Many apologies. This is what I get for running a live demo. There we are. Okay. There have been a few challenges, right? So they've mostly been very few. One is that Scholar is very young. Its benefit is also its curse in that algorithms are kind of optimized for tensor operations. So they can really fly. They can go super, super fast on a GPU, but they don't integrate all the kind of tricks and things like that and optimizations for CPU that something like scikit-learn has. So if we come back to dimensionality reduction, you can do tsne in Scholar. I actually ended up going back and writing bindings to a Rust library because we didn't have access to a GPU on the machine at the time, and the CPU version was very, very slow. So I ended up actually using Rust to go and do that. That being said, that's been kind of the only wrinkle that we've had. Everything has been really, really smooth. I've been kind of shocked at how smooth it has been. Okay, so that's what we've done over the last year. Really quickly, before I run out of time, I am going to talk a little bit about what we have started to work on in starting to think about powering up, right? So we've done. Let's go back. We've transformed our ETL. We've changed the way that we're deploying our machine learning models in production. We have started to be able to build features much, much faster. We're able to deploy features that our customers really want. We're able to prototype in really powerful ways. And we just don't need to reach for libraries in Python or in other languages anymore. We can Rust, but Rust, again, goes through Elixir, right? So we're deploying it with our application. So where do we go from here? I'm going to show you. Something that we've started playing with in our application is text generation with machine learning models. So in this case, what you're seeing is a summary of a patent. and that is a machine learning derived summary. It's saying, okay, this is the problem, these are the solutions and the challenges and things like that. This has been huge for our customers. We do other things with these sorts of models as well. So for example, you're doing your search, you might want to auto-suggest some keywords that might be useful for specifying which patterns you might want to find. Maybe you don't know what the best language is. What you can do is actually have a machine learning model start to understand some of the top results that you've got and the things that you care about, and you can generate keywords. We can go back to that map viz that I showed you before, and you can start automatically labeling these clusters, determining which of determining which labels go to which patterns, right? So if you are an expert in this field, you might look at these and you can get a quick understanding of what the overview is. But you've got to generate those somehow. We're not just going through and doing it by hand. We're using machine learning models to do that, right? Hello. Does anyone know what this is from? Yes? Bumblebee, yes. And so we've started exploring Bumblebee a bit. So we've got generative models that are not using Bumblebee in the application right now. But I'm able to deploy a similar kind of application to what I was showing you with the map visualization or with the time series visualization. I'm able to deploy something like this so that my co-founder, who is much more knowledgeable about patent stuff than I am, is able to go through and start doing prompt engineering, and he's able to actually see our current summary, so what's actually happening in the app. This is connected to a live system, and what the new summary is. So in this case, I'm using Llama 2. This is just for the example. We're just taking it off the shelf and using a model called Llama 2 that Meta put out, and we're exploring how that might be able to compete with our existing generative model. So Livebook has enabled this, given us the ability to connect to this running system, compare and contrast, and in this case, we're able to run Livebook on GPUs. And run local inference and compare it against the remote running system. So that's it. Thank you very much. It's been amazing. Thanks.